4 billion years. It evolved, it mutated, it duplicated trillions of times, but it directly connects you to the first living being on this planet. We could say you touched every living being that came before you with your DNA. But you are more than your DNA. Your body is made of 7 octillion atoms. That's 7 billion, billions. Roughly 93% of the mass of the human body is made up of just 3 elements: oxygen, carbon, and hydrogen. Oxygen and hydrogen are predominantly found in water, which makes up about 60% of the body by weight. Carbon is maybe the most important element for life. It can easily bond with other atoms, which allows for the building of long, complex chains of molecules which make up the solid part of you. The remaining 7% is a tour of the periodic table of elements. Nitrogen, calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iron, fluorine, zinc, copper, iodine, selenium, chromium, manganese, molybdenum, cobalt, lithium, strontium, aluminium, silicon, lead, vanadium, arsenic, and bromine. By the way, this also means you're about 0.5% metal, no matter what your favorite music is. Anyway, these elements perform various functions like enabling oxygen transport, building of bones and cell structures, carrying signals, driving chemical reactions, and a lot more. Your body is in a constant state of transition. Every 16 days, 75% of you has been replaced because a healthy human exchanges about 100% of their water in that time period. Each year, about 98% of your atoms are replaced by new ones, and every 5 years, close to all of the atoms that make up your body weren't there 5 years ago. So, you could call yourself a temporary collection of atoms. But where did these atoms come from? In the beginning of the universe, there were mostly hydrogen and helium atoms. Enormous gas clouds formed over millennia and grew denser and denser until they collapsed under their own gravity, giving birth to the first stars. In the cores of these stars, hydrogen was converted into helium under extreme conditions. After millions of years, the hydrogen became exhausted and the stars began dying. Under super extreme conditions, all elements we know today were created a fraction of a second before they died and exploded in supernovas. They shot most of their contents into space while the cores collapsed and became black holes. All these elements traveled through space for who knows how long, until they arrived at a different cloud that was slowly forming a new star, our Sun. These elements that once were the insides of a star formed planets and found their way onto Earth, where they enabled life to begin. So we are directly connected to the first stars ever born in the universe. We are part of the universe. The idea of being a deeply connected, minuscule part of an enormous structure is really mind-blowing. We don't know what all this means, or if it means anything at all. We know that we're made of little parts that connect us to everything in the universe, to the beginning of everything. And this is kind of a nice thought. You are not alone. You never were. You never will be. It's hard to get to space. As much as we all wish there were an easy and affordable way to see our planet floating in the dark, right now, the only way is to become an astronaut or a billionaire. But there is a concept that might make it possible while serving as the starting point for the exploration of the universe, the space elevator. How exactly does it work? To understand how a space elevator will get us into space, we must first understand what an orbit is. Being in orbit basically means falling towards something but moving fast enough to miss. If you throw a ball on Earth, it makes an arc through the air and then hits the ground. In space, gravity makes you move much the same way, but if you move sideways fast enough, the curvature of the Earth makes the ground fall away beneath you as fast as gravity pulls you towards it. So to enter Earth's orbit, rockets have to go up and sideways fast. By contrast, a space elevator taps into energy from the Earth's rotation to get the cargo going fast. Imagine a child spinning a toy on a rope with an ant on the child's hand. As the ant climbs out along the rope, it starts to move faster and faster as it ascends. Compared to rockets, with cargo launched on an elevator, you only need to provide the energy to go up. fast sideways movement comes free with the Earth's rotation. But a space elevator would, without a doubt, be the single largest and most expensive structure ever built by humans. So, is it worth it? It all comes down to costs. Rockets burn a huge amount of rocket fuel just to get a small amount of cargo into space. At current prices, it costs about $20,000 to put 1 kilogram of payload into space. That's $1.3 million for the average human, $40 million for your car, billions for an international space station. This immense cost is one of the major limitations of human spaceflight. Even with advancing technology, this cost isn't likely to be comparable with the price of an airline ticket anytime soon. A space elevator would solve this problem. After construction, a space elevator is projected to reduce the cost 100-fold to $200 per kilogram. If an inexpensive space elevator costs $20 million, then we'll recoup our losses after launching only 1 million tons, close to the weight of 2 international space stations. So what would a space elevator look like in real life? A space elevator has 4 major components: the tether, anchor, counterweight, and climber. The elevator part of the space elevator is the tether and the climber. It extends from the surface of the Earth to space. The climber is like a conventional elevator carriage, a chamber that works its way up and down the tether. At the base would be an anchor, pinning the tether to the Earth, along with a cord for climbers. At the top is the counterweight, which holds up the tether. The tether is held tight like a rope and supported from above by the tension from the counterweight, located higher than 36,000 kilometers above the Earth's surface. At the counterweight could be a space station, a launching point for all missions from the spaceport elevator. But can we actually build one? It's hard to say. The biggest challenge is the tether. It needs to be light, affordable, and more stable than any material we can produce right now. There are promising materials like graphene and diamond nanothreads, but even they may not be strong enough. And aside from being incredibly strong, the tether will also have to withstand atmospheric corrosion, radiation, and micrometeorite and debris impacts. Additionally, it takes several days to climb the elevator. How do we power climb? It requires a lot of energy to go up. Do we need a nuclear reactor on our elevator carriage? Or do we beam it power from the ground with a superpowered laser? And where do we get the raw materials for a 36,000 kilometer long tether? Do we make it on Earth and launch it into space? Or do we make it in space and lower it down to the Earth? Could asteroid mining be the answer? Put simply, there are still some major technological hurdles to overcome. And a space elevator is not without risk. Should the tether break, it would collapse in spectacular style. If it breaks near the anchor, the force exerted by the counterweight will cause the entire elevator to rise up and send it into space. Should it break near the counterweight, the tether will fall, fly around the world and within the end. The resulting debris in orbit could pose serious problems to future spaceflight. If we build a space elevator on Earth, we have to do it right the first time. For these reasons, some experts have proposed first building a space elevator on the Moon. The Moon's gravity is much weaker than the Earth's, so a flimsier but existing material like kevlar could serve as a tether. Even with all these challenges, the payoff of having a working space elevator would be immense. It might be the first step to truly becoming a spacefaring civilization. Maybe we will never build a space elevator, but in trying to do so, we might learn an awful lot. And when it comes to the exploration of the universe, there can't be too many dreams of a glorious future.
Force of nature, splendid, I respect the right to collect traits, correcting the races, collaborate with the traces. Goodness gracious, I died to go goodbye. I heard so many silence. Bring up a fire, what's up, that is the place that pulls the hold up for a bit, then you move your body like a big monster. I must swing and shake it, making you go. Burn your head, bring them on, move, bring them up. and that's all that it is. This is what the blood and brass race means. Everybody in the place to be. To the beast, not with me. At your maximum tree is my. At the count of three, just scream. 1, 2, 3. I lost my mind and I found it again. And then I lost my mind and I found it again. And I lost my mind and I found it again. Give a deuce, I mean, Tom, teach all those things that come around the room, and feel like it proves, bang, two times change, my old guy, I do it like this was old, because I made what you say, I never looked down the same, what the same, it's all the same, alternative best, make that also my book, seminal, wow, step to the top. Except I have to set correct on the scene.